Assalamu alaikum. This is Akram here, and I teach computer science to ON A-level students. So our today's topic is for A2 class, and this is from their P3 chapter number 1, and this is about real numbers. Real numbers are a little bit different from whole numbers. About whole numbers, you have studied in your ASP1 and how we can convert positive whole numbers or negative whole numbers into their binary equivalent, and how can we come back from binary to their denary equivalent form. This knowledge and understanding of how computer stores such numbers in binary form is of crucial importance, because we know that every type of data that the computer stores, whether it's an image or a sound clip or whether it's some number, it stores in the form of zeros and ones, that is in binary. So carrying on with our discussion, we'll be first converting 37, which is a base 10 number, into its binary equivalent. This will be a short recap of your concepts from ASP1, and it will be a foundation block for our today's lecture. So let's get into it. So let's say computer needs to store 37, which is a whole number, in its storage capacity. So we'll convert it from base 10 to base 2 in order to understand how does that happen. So in order to convert that, I will be using 8-bit notation. This is what you have studied in your P1 in detail. You have converted negative whole numbers into their binary equivalents and positive whole numbers into their binary equivalents, and vice versa. So for now, I'll be converting 37, which is a positive whole number, into its binary equivalent. And in order to write it in 8-bit notation, I will be writing positional significances, which are such as 1, 2, 4, 8, 16, 32, 64, and 128. And in order to construct 37 out of these positional significances, I will be putting 1 under 32, 1 under 4, and 1 under 1. And for the rest of the positional significances, I will be writing zeros. This constructs 37 for me, which is in denary, and in binary, this becomes this. As you all might have noticed, the position significances that I wrote on top actually came from the positions of individual binary digits. The position of this rightmost one is actually 0. The position of the next bit is 1. The position of next bit is 2, and so on and so forth. And the positional significances that were generated based on the idea so whatever the position is, we have to take it to the power of 2, and that will generate for us the positional significance. So for instance, 2 power 0 generates 1 for us, 2 power 3 generates 8, 2 power 5 generates 32, and 2 power 7 generates 128, 2 power 6 generates 64. So whatever the position is, we have to consider that we have to take it to the power of 2 so that we can generate the positional significance. And this scenario actually is from right to left. So this was the scenario that we learned about how can we convert the whole numbers into their binary equivalent. So what does a computer do when it encounters some real number? Real number means it contains a value to the right of the decimal point. So let's take an example. Let's say we have this number for now. It's a real number. Another number, it's also an example of real number. So we'll now study how a computer stores such numbers. We can have a negative real number or a positive real number. So let's consider this second number, and I will explain it to you, the basics. How can we represent real numbers in denary form and in binary form, and what conventions are used in order to write these numbers in both denary and binary. So let's carry on our discussion by using this number as an example. So let me write it down over here. So in real numbers, we have two parts. The first one is Mantissa, which is this whole part, and the other one is exponent. Exponent, as you guys know, is the power. And currently this number is for base 10. So in order to write it down in this form, in Mantissa and exponent form, what I can do is write my original number, and since it does not contain any exponent, so what I can do is write it in this form. So what if I write it down in this form? That means I have moved the decimal point leftward one place. So what it will do, it will add 1 to the exponent, and the exponent will now become 1. And let's say I move even further, and let me transform my number as such. What it will do, as I have moved my decimal point 2 places to the left further, that means it will further add 2 to the exponent. That means our exponent will now become 3. So from this number to this number, what we have done, we have moved our decimal point 3 places to the left. That means we have added 3 values to our exponent, and it became 3 from 0. Another interesting fact about this number is the movement of this decimal point. As I am able to move this decimal point leftward, similarly I can also move it to the rightward. That means I can do this by only varying the value of the exponent here. That means since I can move this decimal point, that means this decimal point can float. This is the reason that the real numbers are known as float point numbers. So generally, in order to write the real numbers using these two parts, we can follow a formula, and that is in this example, this is Mantissa and this is the exponent. In this example, this is the Mantissa and this is exponent. In this example, similarly, this is the Mantissa part, whereas this is the exponent part. And for this example, since this number is belonging to the Denary number system, therefore the base is 10. Whereas when we'll be writing such numbers using Mantissa and exponent notation, the base will become 2. For obvious reasons, because in binary we have zeros and ones. So now we'll be carrying on our discussion to the binary section and how we can represent float point numbers in binary. So it works in the similar manner. We have Mantissa here, we have exponent here. So using these two components, I can write down my float point numbers in binary form using the same formula, and that is Mantissa into base exponent. And currently, since I am working in binary form, the base will be 2. So the formula overall becomes, for binary, so you guys do get the idea that we can use the same formula in order to write down our real numbers or float point numbers in Denary form or in binary form. And in binary form, since the base is 2, the formula is modified as such, whereas while writing down the numbers in Denary form, the base will be 10, and instead of 2, we'll be writing 10 over here. So the Mantissa part in binary has some conventions to write it down. Let me share it with you guys. So we have the Mantissa part. In it, the first bit, which is the leftmost bit, is the sign bit. Then we have a decimal point, which is written as such. Then we have various places, which are known as positional significances. And as you might have noticed, that we are moving to the right of the decimal point. That means the positional significances will decrease. It will be written like that: 2 power minus 1, 2 power minus 2, 2 power minus 3, 2 power minus 4, 2 power minus 5, and so on and so forth. Currently, we have a 6-bit Mantissa. For the sign bit, it can be 1 or it can be 0. If it is 1, as you know from P1, chapter number 1, that is about 2's complement. Since it is the 2's complement form, so the sign bit actually denotes what type of number it is. If the sign bit is 1, then the number is negative. If the sign bit is 0, the number is positive. So it's as simple as that. So if we are moving to the left of the decimal point, which we did in the case of 37, as you might have noticed, the positional significances increased from 1, 2, 4, 8, and 16, and 32 as the power and the positions, which are increasing from right to left, from 1 and up to whichever number we want to go. So for here, as we are moving to the right of the decimal point, the positional significances will not only decrease, so will be the positions. So the position over here is minus 1, so its positional significance is 2 power minus 1. This position is minus 2, so therefore the positional significance of this bit, which might be represented over here, will have a positional significance of 2 power minus 2. If we go on beyond 6-bit notation and we carry on these positional significances, they will continue in the similar manner. So let me write it down before you guys, this whole notation in a simpler format, as you might have to remember it, because you are required to remember that for the examination's sake, and therefore you must have a proper grip. And I will be sharing with you the actual tricks in order to ensure that you make no mistakes and you do the calculations confidently even without calculator. So in order to write the 2's complement form for Mantissa, consisting of fractions, whereas exponent, which is a whole number, let's say we have an 8-bit Mantissa and a 4-bit exponent. That means we have 4 places for exponent and 8 places for Mantissa. Now how can we write the Mantissa in 8-bit notation? So we'll be carrying forward our discussion from here up to this point. So as you know that the first bit, that the leftmost bit for the Mantissa is the sign bit, which can be 1 or 0. If it is 1, then the number is negative. If it is 0, then the number is positive. Then we have other placeholders. So for 8-bit Mantissa, what I can do is, so these are 8 places because we have 8-bit Mantissa. So the leftmost bit will be minus 1. Then we have 2 power minus 1, or it can be written as 1 by 2. Then we have 2 power minus 2, and that is 1 by 4. We have this decimal point over here, 2 power minus 3, that is 1 by 8. So I can continue writing in this manner. So I will be writing 1 by 16, or it can be 2 power minus 4. I can write 1 by 32, 1 by 64, which is 2 power minus 6, and this is 2 power minus 7, or it can be 1 by 128. So in exam, you will be given these places. You will be required to write down these positional significances on top of those. So these positional significances are of much importance to you guys because you have to remember these. So the first bit is the sign bit, and its weight is -1. If it is 1, then we will be considering the value of -1. If it is 0, we won't be considering the value of -1, which is obvious because in computers either it is yes or it is no. So and next we have naruki. And next we have our decimal point, and after that, to the right of it, what we'll be doing is actually decreasing the positions. That means position number -1, -2, -3, pause, चल रहे चल ठीक. So you guys have to remember that the leftmost bit is the sign bit. Its weight is -1. If it is 1, if we have 1 over here, that means we have to consider the value of -1 in our calculations. If it is 0, then the weight of -1 will not be considered. Then we have the decimal point, which will be written as such, and the positional significances are as such: 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, 1 by 64, and 1 by 128. This may go up to 11 places or 12 depending on the requirement of the question. So you guys are just required to multiply the denominator with 2 so that it doubles, because the power of 2 will decrease as we move rightward. So for exponent, since it's a whole number, so we'll be using our concept from P1 about 2's complement. That is, we did whole numbers in detail in that P1. So how to write down 2's complement form of a whole number, and we have 4 places. What we can do is construct 4 places over here and go right to left. First we have 1, then we have 2, then we have 4, and the leftmost bit gets -8 instead of +8 because it is 2's complement notation. And similarly over here, the leftmost bit actually denotes the sign bit. If it is 1, then the weight of -8 will be considered. Otherwise, if it's 0, then the weight of -8 will not be considered. So for fractions, we'll be having this notation, whereas for exponent, we'll be having this notation, and we will be following that. And both of these you guys have to remember because these are required by the examiner in your paper, and it won't be mentioned on top of the binary number which we are provided in the paper. So remembering these is of crucial importance. So up till now we have learned about real numbers, which are also known as float point numbers, because we can float the point leftward or rightward. While moving the point leftward, we'll be increasing the exponent, while moving the point rightward, we'll be decreasing the exponent. And in this manner, we can float the point. Therefore, real numbers are known as float point numbers. And the next point we considered is studying about how we can write the real numbers in both denary and in binary form. And this was what we did when we wrote this formula, that is Mantissa into base power exponent. For denary, this base becomes 10. For binary, this base becomes 2. So this formula, this notation is also of very crucial importance, because by the end of your calculations, you will be needing this formula, because in order to accumulate your answer, in order to accumulate your calculations from these fractions and these exponents, you will be actually combining the two using this formula. So Mantissa from this part and exponent from this part will be actually combined using this formula in order to construct our denary equivalent of that number. So now we'll be getting on with our point number 3, which is conversion from binary to denary, which is the agenda for today's lecture, and we'll be considering this section and merging it with past paper questions. So we'll be actually learning how we can convert binary float point numbers into their denary equivalent using past paper examples. So students, our first example is from October-November 2015, paper 31, question 1. So in this question we'll be doing part A1, and we have Mantissa part as it is written in question. So the Mantissa part is of 8 bits, whereas the exponent part is also of 8 bits. So the exponent is also of 8 bits, and both of these are in their 2C form. And as we have studied before, let's write down the place values. So for Mantissa, the first one is -1. Then we have this decimal point. Then the fractions go in this manner. So each time we go rightward, the denominator gets multiplied by 2. So for this, we'll be having 1 by 16. Then we have 1 by 32, 1 by 64, 1 by 128. And as for exponent, what we have is again the 2's complement, and in order to write it down, we'll be writing the place values as such: 1, 2, 4, 8, 16, 32, 64 and -128. So the leftmost bit becomes negative because it is 2's complement form. So this is the whole number, which is an exponent. This Mantissa is in the form of fractions. So I hope you guys do understand that. So this is where our trick kicks in. Let me write down the trick part. So the first one is consider the rightmost 1 bit in Mantissa the denominator is our overall denominator. So the next step is from that rightmost 1 bit, go leftward, writing the values as 1, 2, 4, 8, and this may continue. And if the place value is -1, which is this, the value which we are actually inserting, the new value, will be a multiple of -1. So you guys don't need to worry. We'll be discussing these steps in detail. And point number 3 is for the values from step 2, wherever there is a 1, we'll be adding those values to construct the numerator. So guys, let's apply these steps on our example of Mantissa. So as we go rightward, our rightmost one is actually at 1 by 16. So as the rule number 1 states, wherever is our rightmost one, that will be our overall denominator for our Mantissa. The next step says, from that rightmost one, go leftward, placing the values as such 1, 2, 4, 8, and if the value on top is -1, we'll be writing the value which we are aiming to write as a multiple of -1. So for this, I'll be writing 1 over here, then 2, then 4, then 8, and then -16. I'm writing -16 over here instead of +16 because on top I have -1. This is what this rule says. So the rule number 3 comes in. So wherever we have one bit, which is this and this, so we'll be writing those values, which is 4 plus 1, and adding these up to form our numerator. So our overall Mantissa is 5 by 16. So just like that, you have your Mantissa. So our exponent was also of 8 bits, and as given in the question, it is so since exponent is in 2C form, so we can go on like that, placing the place values 1, 2, 4, 8, 16, 32, 64, and -128, because the leftmost bit in 2's complement is a -1. So we'll be only adding up the place values wherever we have ones. So we have 1 at 2 and 1. So as a whole, this constructs our exponent. So as you guys do remember the formula for calculation, Mantissa into 2, which is the base 2, because we have binary numbers over here, and power exponent. So over here our Mantissa is 5 by 16, whereas 2 power exponent, which is 3. So this constructs us our number, that is positive 2.5, and this is our answer. Okay, so now we'll be getting on to our next example, that is from May June 18, P31, question 1. So over here the Mantissa is of 12 bits, whereas the exponent is of 4 bits. In order to resolve the Mantissa, I'll be writing the place values -1, 1 by 2, 1 by 4, 1 by 8, 1 by 16, 1 by 32, 1 by 64, 1 by 128, 1 by 256, and the next one will be 1 by 512, and the next one is 1024, and I don't need to go beyond this because I don't have any 1 bit beyond this place. So guys, let's apply our trick part, and that is first finding the rightmost bit, and this is 1 by 1024. So the second part is, second step is placing 1 underneath it and then going leftward, placing the values as such: 2, 4, 8, 16, 32, 64, 128, 256, 512, and for -1 it will be -1024 instead of 1024. So I'll be writing it as such. So wherever I have 1, I'll be writing those place values. So categorically it is -1024 plus 256 plus 128 plus 64 plus 8 plus 4 plus 1, and our overall denominator is 1024, as it is our rightmost one placed there. So now the overall answer for Mantissa is minus 563 over 1024. Whereas for exponent, we'll be going on like that, 1 2 4 and then minus 8, because for 2's complement we'll be placing leftmost bit as the negative one. So this is minus 8. So overall our exponent becomes 4 plus 1, that is 5. So let's write down our formula and get done with this calculation. So our exponent is 5, whereas our mantissa is as it is given over here. So 1024 is basically 2 power 10. Whereas we have 2 power 5 over here. This will be cut with this, and overall answer is minus 563 over 32. And this is our actual answer. So as you guys have noticed, let me revise it for you. So we first of all we locate the rightmost one, and that is our overall denominator for the mantissa, and then we go on placing the values as such leftward, going leftward, and then we have 2 4 8 16 32 64 128 256 512 and then minus 1024, because on top we have minus 1. So wherever we have 1, we added those up to construct our numerator. Then we get on with our exponent and calculate it as such, and using the formula we have calculated our value. So as you guys might have noticed, this whole fraction addition has been summed up to some easy approach. So I hope you guys would have understood how we can convert binary float point numbers into their denary equivalent, and this can be carried forward that we can convert denary float point numbers into their binary float point equivalents. So that would be all for today. Thank you very much.